On the right side of the board is what's in your notes, but we're going to use that today, so I put it back on the board for us. You've got a hard copy of the Moody diagram in your hands from last lecture, and you've got a Moody chart in the textbook, or your e-version of that. And it's on also your tables for the final that I gave you. So you'll have the Moody chart on the table for the final. Okay, there's two ways we talked about them both. Graphically, we have the Moody chart. If you're in the laminar range, I wouldn't even bother to use the Moody chart because it's very simple to calculate F. It's 64 divided by the Reynolds number in the laminar range, less than 2100. If you're in the turbulent range, there's different lines to follow. Each of the set of lines, the family of lines, offer different relative roughnesses. E is the roughness, D is the diameter. E over D is called a relative roughness because it's dimensionless. The friction factor is dimensionless. The Reynolds number is dimensionless. The Moody chart is a dimensionless graph. If it's a smooth pipe, the roughness is 0, we assume. So for instance, like a PVC sprinkler pipe, very smooth to the touch, slippery almost to the touch. We can approximate that as a smooth pipe. E is 0 for that. And on the Moody chart I gave you, there's a little legend there which has different roughnesses, values of E in both SI and British gravitation. Riveted steel, concrete, wood, cast iron, galvanized iron, wrought iron, drawn tubing. So you have a whole selection of different pipe materials that you can get the value of E for. And the way that you use that, just to do a quick review, is we calculate the Reynolds number. First, that's number one, as we said, in a fluid flow situation, a pipe, it's always a good thing to do, calculate the Reynolds number first. That's your first decision. Is it laminar or is it turbulent? Okay. So I'm giving you an example here. I've got a smooth pipe, maybe PVC. Reynolds number, 100,000. And I go to the Moody. Moody chart, I get F equal 0.0179. One times 10 to the fifth. Over here, I go up here. Smooth pipe, I go horizontally across. 0.0179. Both axes are logarithmic. They can be somewhat difficult to read. You have to be very careful. Can I read 179? Well, if my eyes are really good when I'm reading this. I can see 0.015, 0.016, 0.017, and 0.018. So I just approximated. It's somewhere between 0175 and 0180. You can't read super accurately. Probably just the 2 sig figures, maybe 3. I could read 175, I think, from that graph. 179, I think I'm really close to 180 if I look at it again. Okay, now you also can use this equation which fits, notice what it says, everything non-laminar except the critical zone. Don't forget this zone right here, we have no equations, we have no graph for that. That's a no-fly zone. Don't want to end up there, so stay out of there. Okay, to the right of that line of 4,000, that's the non-laminar. What's it composed of? Well, if you look at this Moody chart again, is composed of two regions. One is called completely turbulent region. That's where these lines are flat horizontal. Where they curve back up to the left, that's called the transition region. So there's a transition region and a complete turbulent region. The smooth pipe never does end up horizontal, never does. It's always coming down this way. Okay, so that's okay. This fits it. For a smooth pipe, put E0, E is 0, smooth pipe. So use the equation for a smooth pipe. E equals 0. You can back F out of that, and I end up with 0.0178. So it's in really good agreement with that. So the smooth pipe curve equation seems to fit the Reed and Moody chart very well. Okay. Let's take 2-inch galvanized iron pipe. Okay, water, it's water. By the way, this was also, you didn't know it was water, that's fine. This is water, we'll need to know that in this one. With a velocity, average velocity of 10 feet per second. Okay, step number 1, as we said, get the Reynolds number. Velocity 10, diameter 2 divided by 12. Kinematic viscosity in the textbook. Reynolds number 1.38 times 10 to the 5th. The value of E over D on the Moody chart. In the legend it says if it's galvanized iron, in feet E is 0.0005. The diameter, 2 divided by 12, 0.16667 feet. 0.003. Moody chart. F equal 0.027. So I go over here. I find the line E over D 003. There's a 002 and there's a 004 on this graph, which means you have to interpolate. Okay, so go halfway between is fine. Take your pencil, maybe draw a line along there between the 002 and the 004 on the E over D. The Reynolds number is 1.4 times 10 to the 5th. So it just started up from being horizontal. So it's right around here. Here's E over D equal 0.003. Read across horizontally. And I've got from the Reed and Moody chart 0.027. Yeah. And if I use the equation, F comes out to be 0.00025. So again, we're pretty close. We're pretty close. And I've given you 3 examples on the handout of how to find F. So you got tons of examples on how to find F for a particular fluid, a particular pipe, a particular geometry. Geometry is the diameter. The fluid is kinematic viscosity. The kinematics is the velocity. So velocity, diameter, and the properties of the fluid. Okay, so that's how you can use that. Now, let's take a look at what kind of problems we can have with these pipe flow type problems. This is in the book, but I'll put it on the board here also for you. Three types of problems. We'll do category, and then we'll do what's given, and what the unknown is. There's a category 1 type problem, a category 2 type problem, and a category 3 type problems. Okay. This is like a category 1 problem when I worked here. I'm given, for instance, Q, the flow rate, the diameter, the relative roughness, and the kinematic viscosity. And I'm asked to find the head loss. Okay, so what do I do? Well, okay. I take Q and I divide it by the area, pi d squared divided by 4. That gives me the velocity. So I know the velocity. I know the velocity. I'm given the diameter. I know a diameter. I'm typically given the length too. So I know the length. I know what the fluid is. Let's just say it's water at 120 degrees Fahrenheit. Okay, I know nu. Got it. Do I know the Reynolds number? Of course I do. Do I know E over D? Of course I do. What do I do if I know the Reynolds number and E over D? I go to the Moody chart. From the Moody chart, what do I find? The friction factor. Where do I use the friction factor? I put it up here. And what do I calculate? HL. That means the head loss due to friction in the pipe. Okay, second kind of problem. Now I don't know Q, unknown. But I do know the pipe diameter. I do know epsilon. I do know nu. And I do know H sub L. Okay? So, let's put up here again, put a check mark by what we know. I do know diameter. Got it. Got it. I do know epsilon. Okay, so I know E over D. Got it. I know diameter, so I know the relative roughness. I do know kinematic viscosity, nu. I know the pipe length, L. Oh, I know H sub L. H sub L, got it. Okay. The Reynolds number. I don't know it because I don't know the velocity. Here, The unknowns, F and velocity. I don't know velocity. I can't solve for F or the velocity. Conclusion, uh-oh, we got a problem. We don't know the Reynolds number. How do I use the Moody chart, or how do I use this if both these guys are unknown? You can't solve that one equation. Okay, this is called a guessing game. If you don't know it, guess it and start the calculation, and it will be iterative in the end. So I guess NF. This problem here is guess F and iterate. I'll just put it here, over here. All right, I guess an F. If I guess an F from over here, I'll put the F up here. With that F guess, I'll calculate the velocity. With the velocity, I'll calculate the Reynolds number. Okay, I guess the F, and I can now find the Reynolds number and F. But take the Reynolds number. Go over here. With that Reynolds number you got with the F guess, go up to the E over D line, go across. If the F you get doesn't match the F you guessed, try again. Repeat it with that new F guess. Guess F, get Reynolds, go to Moody, find F. If they don't agree, repeat above until F converges. It's an iterative solution. You guess F from the Moody chart. You put the F in up here. You get the velocity. You put the velocity in the Reynolds number. Now go back to the Moody chart with that Reynolds number and that E over D. See what F comes out. If the F that comes out of the Moody chart doesn't agree with the F you guessed, repeat the calculation with the second F you got. It'll eventually converge. Where do you want to guess F? Well, let's say you're on this line right here, E over D. There's an E over D line. What am I going to guess for F? I'm going to play the odds. I think it's really turbulent. I'm going to guess F where that line is horizontal or flat. That's my first F guess. So I go back here, and that's my first F guess. Where the E over D line becomes horizontal. You're playing the odds. You think it's going to be turbulent, really turbulent? Why not? Why guess there? Why guess there? It's probably going to be out here somewhere. And if not, that's okay. We'll converge. One or two times we'll converge. What if it's a smooth pipe? If it's a smooth pipe, all bets are off. Does it ever get horizontal? No. What's a good F guess? Well, I don't care. Close your eyes and walk up there. There, I think right there, that's good. Conclusion, a good F guess for smooth pipe is probably in the middle, from here to here. Somewhere in the middle is my first guess, from here to here. Right here, maybe .030. It won't matter. It's going to be iterative. It's going to be iterative anyway. Yeah.
If say in the first try you got lucky and your answer's really close to what it is.
If you're within .001, stop.
Okay.
.001. That's the readability of the Moody chart.
Okay.
Stop. Now, here's the deal. On an exam situation, I don't want you to get a rating. Time's too much of a factor. On an exam situation, you tell me what your first guess is. You go through it one time. You go to the Moody chart. You find out what the F comes out here. It didn't agree with my F guess. You say, .027 didn't agree with my first F guess, .030. I would repeat the above calculations based on Tell me what you're gonna do based on .027. But don't do any more work. Don't iterate, but go through it one time to prove to me you know what you're doing in the iteration process. Okay. All right, let's do the last one then. The last one, somebody says, how big should the pipe be to carry this oil with a pressure drop of 1,000 pascals per meter? So you don't know how big the pipe diameter is. So what do you know? You know Q, E, nu, H, L, that's it. I don't know diameter. All right, let's play the game again. I don't know the diameter. I know E, I know nu, I know V, I know V, I don't know D, I know L,
Wait,
I don't know F.
how do you know V?
Oh, I'm sorry, yeah. Yeah, I don't know V, thanks. I need my, there. Okay. Now we get to the real guessing game. Okay, let's start this thing, and you can, what you might want to do, you can guess D. I mean, any of these things, you can guess what you want. You can guess, what were the unknowns before? The Q and the F and so on. Just guess something. In this particular case, let's see what I guessed on this guy. I guessed F again, so there's a reason why. Guess D, I've got it. I've got it. Put it in there. Okay, I know HL. Okay. I know HL. Oh, I know HL. Okay, so I can guess that. On your F, you can guess F again, or you can guess D. What are you going to guess for a pipe? What's the possible diameters? I don't know, maybe 1/8 of an inch to 36 feet? Wow, that's a wild guess. You'd be converging for hours. No, it's easier to guess F on the Moody chart. Just pick a middle value out. I don't know what D is, I don't know what Reynolds number is. What's my first guess? I don't know, .030. Fine. Once I guess that, I can come back to Moody chart, get a Reynolds number, get an E over D, come up here, go over there, get an F, and check it against my F guess here. So that's a little more difficult iterative process. But one that occurs, it occurs in the real world. How big a pipe should I specify for that job? Okay, so anyway, that's the part 2 of what I gave you. So here's what I gave you last time. On the handout I gave you, example 711 is category 1 problem. Example 712 is a category 2 problem. Example 713 on the handout is a category 3 problem. So you have an example of every one of these 3 problems to follow. Now here's the good news. Okay. On that page 2, on the right left-hand column, read it here. An alternative to using the Moody diagram that avoids any trial and error process is made possible by empirically derived formulas. Now, empirical comes from observation. They're not derived theoretically, empirical. Presented by Swamy and Jain, 1976. This appears in our current textbook. It's a long time ago, but they still work. For pipe flow. An explicit expression that provides an approximate value for the unknown in each category problem. So you've got 3 equations. One equation that works for category 1, one equation works for category 2, one equation works for category 3, and it tells you when they work. Category 3 problem. E over D must be between 1 times 10 to the minus 6 and 1 times 10 to the minus 2. Reynolds number must be between 5 times 10 to the 3 and 3 times 10 to the 8. Ooh, that's a big region. That's a big region. 5,000, 5 times 10 to the 3rd, right here. All the way where? To 10 to the 8. Way out here. That's a good range. And it says, below that it says, and by the way, you can use either English or SI in these equations. You can use either English or SI in these equations. And then, the examples I gave you, I told you, I gave you 3 examples. First of all, they work it by guessing and the Moody chart. Second of all, they work it by the equations on here. This category problem, for instance, this example 713, they solve for what? Diameter. If they do the guessing game on that, their first guess what? 0.03. What did I say? 0.03. That's a good guess, Dominic. You don't know anything, guess 0.03. They guess 0.03. It converged in 2 iterations. It's on the handout. It converged in 2 iterations. What was the diameter? 4 centimeters. Now put it in the approximate equation. Guess what they get? No iteration required. 3.9 compared to 4 centimeters. Close? Oh, of course it's close. Which one's right? Neither one's right. It says right there, the equations are approximate, and we know the Moody chart's only accurate to 10%. 10% of 4 is what? 0.4? Wow. Wow. So yeah, these guys are right on together. It gives you some confidence then in the equations will work with the iterative procedure. Okay, so you've got those possibilities, okay? If I give you an exam problem like that, you can do one of 2 ways. You could use the equation, which is pretty complex, but you can use it on, you know. Or if you want to make one guess and then go through it one time and tell me what your next guess for F would be, that's fine too. Your choice. Okay, now, if you didn't get the handout last time, see me after class. I've got a couple extra copies here. All right, now, let's go back and see where we use this information. Okay, and you know we use it in the energy equation, so I think I'll put that over here. All right, let's write out the head form of the energy equation one more time. All right, so we have our left-hand side, energy added to the system, our control volume. So we have P1 over gamma, V1 squared, Z1 plus the head developed by a pump, subscript 2, turbine, if there's one, straight pipe friction losses, and minor losses. Just to remember again, that guy, of course, works for laminar or turbulent. Of course, the F depends on laminar or turbulent, but the equation works for laminar or turbulent. Okay, we haven't done HM. HM stands for minor losses. The reason why it's called minor losses is because for most large piping systems, those losses are somewhat minor compared to the straight pipe friction losses. H sub L. Normally in a big pipe network, maybe a petrochemical plant, maybe a steam power plant, these guys are much, much less than this guy. This guy's a straight pipe friction loss. This guy is the loss due to fittings in a pipe, an elbow, a T, a valve, things like that. So we'll put down elbows, T's, valves, etc. Those are all components of the piping network which do add some resistance to the pipe flow, and they're called the minor losses, which is a misnomer because many times they're pretty big. But because this stuff is done for larger plants, typically they're minor losses. But they can be as big as HL. They can be as big as HL. Okay, where do they come from? Okay, well, here's a handout that shows you some of these guys. They're in your textbook, of course, too. You'll have them on the final exam. They're in your equation package I give you, so they're available for you on the final. Don't put them on your equation sheet. One more? Okay, I'll be back in a minute. I don't think this is the same table as in your textbook. I like this one better, but the one on the exam handout equation package is, I think, the one in your textbook. Let's see, one more over there. Okay. We're going to work example 715 just a minute, but so drop down the middle of the page. The middle of the page gives you a table which lists various type fittings in a pipe network along with their K value. Now let's get the K value down. The minor losses are expressed as the summation of K's times V squared over 2G. It looks a lot like this guy, except in front of the V squared divided by 2G, we have a summation of K's. The K's are called the minor loss coefficients. They're pretty much constants. They're constants. You search them out and find them and add them together in the pipe network. From where to where? Typically from point 1 to point 2. Wherever you write the energy equation, go from point 1 to point 2 and find all the minor losses in that path. Okay, well, here we are. Let's go down to an elbow. There's an elbow. There's a standard elbow, a long sweep elbow, a 45-degree elbow. Then there are two kinds of connections, a screwed connection for a pipe or a flange connection for a pipe. Under the screwed connection, the diameter 2.5, 5, 10. Under the flange, 5, 10, 20 centimeters. Then you have different kind of valves. By the way, there's a T, two T's, a branch and a line. A branch and a line. Here comes a flow into a T. Some of it goes that way, some goes down that way. If the flow goes here to here, that's line, the main line. It's a railroad track, that's the main line. The branch railroad track makes a right turn, that guy. So if your point here is 1 and your point here is 2, you use the line value. If your point 1 is there and your point 2 is here, you use the branch value. Where do these things come from? Oh, they came from experimentation. We've got a whole setup in the fluid mechanics hydraulics lab. You can go down there and put anything you want in our pipe network and find the K value. Matter of fact, that's one experiment. A globe valve, a gate valve, a swing check valve, a filter, all those things. You can find the K value. What do? Take a piece of horizontal pipe. Okay? These two guys cancel out. These two guys are 0. There's no pump. There's no turbine. Account for the short piece of pipe between your two pressure taps. So if this is your two pressure taps here, here's a valve. You put a pressure tap in here, pressure tap in here. If the pressure taps are close to the valve, then there's really no straight pipe. So he's gone, these guys are gone. That says HM is equal to P1 minus P2 divided by gamma, and HM is equal to KV squared over 2G. You measure the velocity with the flow meter, I've got it. You measure delta P with a pressure transducer, I got it. You know what's water at room temperature, I got it. What do you solve for? K. K values in that table came from that method of experimentation. Okay, so anyway, they came from experiments. There. They can vary dramatically, you know, plus or minus 30, 40, 50%. Because everybody makes things a little bit differently. Valve manufacturers, filter manufacturers. Anyway, back to here. Globe valve. Is it fully open, half open, or 1/4 open? An angle valve, fully open. A swing check valve, fully open. A gate valve, fully open. A return bend where it makes a 180. Return bend is in there. All those things are, what if you can't find it here? Well, go search it on the line, on the internet. Go search it, you'll find it somewhere. Search it out. If it's not in here, you're the engineer, you go out and find what the K value is for. If you can't find out, you might run a test on it and see what the K value is. But you'll probably find it. Oh, a square-edged entrance from a reservoir to a pipe, 0.5. A reentrant entrance where the pipe sticks into the reservoir, 0.8. A well-rounded entrance, very smooth, K, 0.03, really low. Look at the K for a globe valve, 1/4 open. Wow, 50. 50, big time pressure drop. Okay, 60 for a flange one, 60. Okay, all these things are here then, okay. What if your diameter is, by the way, it says screwed 5 inches, that's a misprint, that's centimeters. So I'm gonna change that to centimeters. Under screw connections, 5 inch, it should be 5 centimeters. What if you've got something that's 7.5 centimeters, and you say, well, it's not on there. You're the engineer, you know. What you do is you plot K versus diameter. There's 3 values given there. Here, here, and there. Take your best guess on Excel. Draw a line through it. There you go. Now find 7.5. Don't interpolate linearly unless you know it's linear. No. Plot the values and then go to the diameter you have and read across, because you'll find out they're not linear. They're not linear. Okay, so that's how you find the K values for different diameters than on that sheet of paper. Okay, so that's what we do with that. Now let's take a look at the example problem I've got there, which is the one that's above it. So you can, this is just so I don't have to write this on the board and have you copy it down. But I'll put it on the board, but you don't need to copy it down. Let's leave that equation up there. Okay, let's get rid of this. Let's get rid of this. And I'll draw the picture up here just so that we can follow on the board. We have 2 reservoirs with water at 20 degrees C. Okay, so reservoir 1 is up here, water at 20 degrees C. Going into a pipeline, because this makes an elbow down here, elbow here, ends up down here. This is H. Capital H. Okay. There is a screwed globe valve fully open right here. I'm not going to put all the details on it. It's fully open. 20 meters from here to here. 10 meters from here to here. And 20 meters from here to here. Of course, the water's going to be flowing down from the upper reservoir to the lower reservoir, so the flow direction is like that. The pipe is wrought iron. It has a diameter of 10 centimeters. The flow rate Q is equal to 0.04. Oh, and let's see. Yeah, find H. Okay, so we're supposed to then find H. Given E, D, L, Q. Find H. Okay, I know right away. That's a category 1 problem. I don't need to iterate. I don't need to iterate.
What's E again? Little E?
I'm sorry.
What's little E again?
This one?
Yeah.
That wrought iron tells me that's that.
Okay. All right.
That tells me that. That tells me that. That tells me that. So when somebody says, I'm giving you the pipe material, you know they're saying, I'm giving you E. If somebody says to you, I'm giving you the volumetric flow rate with the pipe diameter, they're telling you, I'm giving you velocity V. Do I have Q? Yes. Do I have diameter? Yes. Can I find V? Of course. Okay. Now, let's go back to here again. Of course not. Don't put .1 down there. No, bad choice, bad choice. Put .1 where you know the most stuff. The pressure is 0. The velocity is 0. And the elevation is capital H. Oh, okay. 0. 0. Capital H. All right, H. Is there a pump? No. 0. Is there a turbine? No. 0. Is P2 0? By the way, point 2 is over there where it's going to end up. 0. Is V2 0? Yeah. Is Z2 0? Yeah. Okay, so our H is equal to, there's H right there. H is equal to HL plus HM. Okay. So, now let's see. There we are. All right. Well, let's get the velocity. All right, I'll put that right here. Velocity equal Q over A, 0.04 divided by pi over 4. Diameter is 10 centimeters. Pipe velocity, 5.09. You see there's 3 velocities in the energy equation. There's V1, there's V2, and there's plain old V. Plain old V, no subscript, is the average velocity in the pipe. That's how we get it. The volumetric flow rate divided by the pipe cross-sectional area. Number 2, get the Reynolds number. V, D over nu is water. Velocity, 5.09. The diameter, 0.10. Kinematic viscosity, 1 times 10 to the minus 6. And that gives us 5.09 times 10 to the fifth. Okay, I'll put E over D up here. E over D. Go to the little menu on the Moody chart and find for galvanized wrought iron. Okay, find wrought iron. There it is. So 0.046 divided by the pipe diameter equal 0.00046. Now, of course, you know, if I go out and buy a steel pipe, and I buy a 1-inch steel pipe, is that 1 inch the inside diameter of the pipe? No. It's Schedule 40, by the way. Is the 1 inch the outside diameter of the pipe? No. Conclusion, a 1-inch pipe doesn't have an ID of 1 inch and doesn't have an OD of 1 inch. That's why it's called a nominal pipe size. Nominal. If you want to know the actual ID, and this cube should be based on, of course, the cross-sectional area where the water flows. That's the ID. You have to go to a pipe table, and a pipe table tells you, for a Schedule 40 1-inch pipe, here's the ID, here's the OD. But in this class, we're not going to worry about that. That's just a sidelight, just so you know when somebody says a 1-inch pipe, be careful. Don't use 1 inch unless you know the ID is 1 inch. Okay, in this class though, if I say that's the pipe diameter, that's the inside diameter. Everything I say will be the inside diameter of the pipe. Okay, go to the Moody chart with the Reynolds number. 5.1 times 10 to the fifth, right here. Go up to the right line for E over D, label 0.3046, it's down here somewhere. Go across horizontally, always go across horizontally. Once you find the intersection, go across horizontally until you find the friction factor. And from the Moody chart, it's 0.017, if you want to exaggerate, 3. Okay, now we get the minor losses. Summation of the Ks. All right, so first of all, the water comes out of the upper reservoir. It goes into a pipe. Okay, look at the minor loss table. A square edge entrance for a reservoir to a pipe. K is 0.5. Entry. We're going to assume square-edged unless told otherwise. You could make it like a well-rounded one, but that's expensive, not normally done. So unless it says well-rounded, assume it's always a square-edged inlet, 0.5. By the way, the water comes out of the pipe and goes into the reservoir here. Exit. Pipe exit, 1. It doesn't matter if it's square edge or rounded, it's 1 plus 1. Now we go through a valve. What kind of a valve told us that the valve was a screw blow valve. So go to our page, blow valve, screw blow valve, wide open. Okay, wide open. The pipe diameter was 10 centimeters. So the glow valve fully opened 5.7, I guess it was. Okay, that's screwed right, 5.7, fully open glow valve. All right, and now we've got 2 elbows, here and here. Unless you're told otherwise, always assume they're standard elbows. Always assume standard unless you're told otherwise. So standard elbows, 0.64 plus 2 times 0.64. So the summation of all the minor losses in that pipe network come out to be, let's see, okay, that's 1, 2, 8, and 5.7, and 1.5. 8, 7, 8, 9, 10, 14, 5, 6, 7, 8. 8, 9, 10, 14, 5, 6, 7, 8, yeah. Okay, so those are the summation of the case. All right, go back over here. Do what it says. H equal F L over D V squared over 2G plus HM summation of K's V squared over 2G. And let's see, we have 11.4 plus 11.2, which is 22.6 meters. If you plug in that F over there and plug in the K's and multiply by V, it's all here, V squared, 5.09 squared. I won't go through all the gory details. That's what it is. Yeah.
Is the length for the
Oh, yeah,
losses,
thanks.
is that
I will put that in, yeah, thank you. I meant to mention that. It's everything from point 1 to point 2, a straight pipe. 20 plus 20 is 40, plus 10 is 50. Yeah, thank you. Okay, now, as I told you before, they're called minor losses because normally they're not as big as the straight pipe losses. Not here. They're about the same. They sure aren't minor, don't neglect them. Why is that? Because the pipe length is only half a football field, 50 meters. Okay? So the straight pipe loss is about equivalent to the loss through that valve. The valve's a big guy. Look at the valve. There he is. What's the problem in that line? That valve is causing a big pressure drop. So yeah, you can look at the minor losses and say, what should I improve? Well, I don't know, maybe change the valve. That's the biggest loss there. So you can do things like that. Okay, now, the last one we're going to work today. Okay, so now I say, you know what? I want to pump the water from the lower reservoir to the upper reservoir. I add a pump. And I'm going to use the same conditions. So now add a pump. Keep all other inflow the same. Is there a valve? Yes, there still is. Are there two elbows? Yes, there still are. Is there still 50 meters of straight pipe? Yes, there is. Is the pipe wrought iron? Yes, it is. Is it 10 centimeters in diameter? Yes, it is. Is the Q .04? Yes, it is. Everything is the same. I take the answer from the first part, which was 22.4 meters. I put that in here for H, and now I want to see how much power has to be provided by that pump to the water to do the job. So find the power needed by the pump. Okay, start again. There's a picture. Yes, 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 valve, yes, water, yes, wrought iron, yes, 10 centimeters, yes, Q, yes, and now H, 22.4 meters. 22.6. Okay. Go back here, say, you know what, I can't do this now. There's a pump in there. Leave that guy in there. Yes, yes.
0.
Okay, let's put point 1. You gotta flip your points now. For the first problem, point 1 was up here, point 2 down here. Why? Because that's the way the water flows. Now I put point 1 here and point 2 up here. Why? Because that's the way the water flows from 1 to 2. Okay. P1 0, V1 0, P2 0, V2 0, Z2 H 22.6. Z1 lower reservoir 0. Still minor losses. Of course there's piping. Are still pipe loss? Yes there is. Still minor loss? Yes there is. Valve, 2 fittings, entrance, exit, so on and so forth. Okay, there it is. HP equals Z2, 22.6. I'll put H in there. Plus F L over D, V squared over 2G, plus summation of K's, V squared over 2G. Okay, go ahead and put the numbers in. 22.6 plus. I erased it, but I've already done that. Did F change? Well, let me ask a question. Did the Reynolds number change? No. Did E over D change? No. Is F the same now as for the first problem? Yes. Okay. F didn't change. Did I change any of the valves, or the elbows, or the entrance, or the exit? No. What's the summation of K's? It didn't change. Did the velocity change? Nope. I said Q.04. B didn't change, K didn't change, V didn't change, L didn't change, D didn't change, F didn't change, so take the numbers from the previous problem. 11.2 and 11.4. So now the head that must be developed by the pump, 45.2. Let's talk about the energy that the pump provided. The pump is being driven by a motor. The pump is trying to do something to the fluid. What's it doing to the fluid? Number one is it's raising its potential energy from point 1 to point 2. Okay, there it is. What else does the pump have to do? Oh, it has to overcome friction because there's friction in these wrought iron pipes. There it is. Oh, and by the way, there's a valve, 2 elbows, and an entrance and an exit. It has to overcome that loss. That's a loss of energy. So the pump, the power the pump needs must raise the water level, it must overcome friction, and it must overcome minor losses. That's what it means. Okay, now we know the power. W dot power is equal to gamma Q HP. You know gamma, you know Q, it's given 0.04, and you know HP, 17.7 kilowatts. Which comes out to be, if you convert that, 39.6 horsepower. You probably use the 40 horsepower. I mean, it's 40 horsepower needs to be driven, but the motor, of course, is more than that because of the inefficiency of the pump. So anyway, the power the pump must provide to the water is 17.7 kilowatts. So we work the problem each way like that, which is a good thing. Okay, any questions on that? All right, now, I think we are officially done, except when we're done, I've got all this homework that hasn't been picked up for the quarter. So if you're missing any homework or exams, it's in the stack. So it's up here in front, and otherwise we'll see you Monday afternoon. Get a good night's sleep and a good lunch. Not too much. And we'll see you then.